Just imagine you're just looking outside your window and you see a tree. Okay, the first day you see it at that position, and the second day you see it at the position, and the third day on the evening you see it in the same position. On the seventh day at the morning you again see it in the same position. So you can say the tree does not change its position with respect to the immediate surroundings and time. So you declare that the motion, state of motion of the tree is at rest. But if I try to analyze this, try to represent it graphically, then how it looks like. Just think what I have said. To fix the phenomena of immediate surroundings, we consider a reference point. And now we consider reference point is U. And the object you want to observe, that is a tree. So you are measuring the position of the tree with respect to U. So you are the reference point here. Each and every day you are standing at the same positions on your window and try to look outside towards the tree. On the first day, I want to say, the first day it is at this position. This is the observations on the first day. Now if you're looking at the second day is the position vector with respect to you. You are the reference point here. It is at again the same position. Now on the third day, position is like this. So on the fourth day and go on, we get the position like here. So if we try to connect all these points here, what it will represent? It becomes a straight line which is parallel to that of the time axis of the position versus time curve. So in the position versus time graph, it shows a parallel to that of the time axis. The graph is parallel to that of the time axis. So these basically represent any object which is at rest. Why? Because with the changing time, the position is not changed. Now I want to say that then what is displacement? The displacement is defined as somehow like this. Displacement is defined as RF minus RI with respect to the final position, with respect to the origin or reference point, the position vector of the final position, with respect to the origin or reference point, the position vector of the initial position. If we subtract this, then we get the displacement. So it is RF vector minus RI vector. So this is basically the displacement. So if I want to say what is the displacement of the tree, now you say, is it moves? Is it move with respect to time? So that there is no question of moving from the initial position to that of the final position. It is not actually moving. We can say mathematically that initial position and the final position is the same with the increasing time. As the time goes on, obviously the trees is not cutting down, or trees just uprooted due to some storm or something. So if it will be at that particular position, then the initial position, the final position that you are observing at several time intervals, just like on the first day, if you say it is the initial time, then on the second day it is the final time, no position is changed. So the difference between the position vectors will be 0 vector, null vector, that is not changing. Since that is not changing, so if I want to represent the displacement with time, now I am representing the displacement with time. So for the first day, second day, first day, second day, if you say the third day and fourth day, whatever be it, the displacement is 0. So what we can say that the curve is now parallel to, not only parallel, it is on the time axis, and it is parallel to that of the time axis. So we are basically trying to project the same scenario. In the first graph, we try to project the position vector of an object, how it changes with time. We try to understand this thing, and we have seen it is not changing, and the position vector is parallel to that of the time axis. Now if I try to draw the displacement versus diagram of that particular object, it is also representing the rest. It is also representing the rest. Okay, so it is parallel to that of the, not only parallel, more specifically, it is along the time axis.